Good morning, students and viewers. In this video, we are going to see the thermodynamics topic, Thermodynamics II, and we have some more about the thermodynamics of one in the studied in the previous classes, in the previous years, because now we are going to discuss the thermodynamics II. Thermodynamics 1 actually represents the flow of heat, a flow of heat from one form to that can be converted from one form to another form. The energy can be transferred from one form to another form without any loss. That is, a conservation of energy is the first law of thermodynamics. Now we are going to see the second law of thermodynamics. So why we needed the second law of thermodynamics instead of discussing the first law of thermodynamics? Because first law says that the conservation of energy, that means the energy can be transformed, but in the case of second law of thermodynamics, we need the how much of heat absorbed that converted into equal amount of work. So what is the first law? How much amount of heat is absorbed that can be converted into equal amount of work. But in this case, first law is failure to explain some of the concepts here. The first one is the direction of flow of heat. So how the flow of heat from transferred from one direction to another direction. Suppose we can say another way, it is impossible to extract heat from ice by cooling. So this is one of the failures. So we need the second law of thermodynamics. The second point is energy of an isolated system. So energy of an isolated system remains constant during the reactions because the energy cannot be transformed from system to surrounding. What is a system? It is a physical distinct part that can be separated from the surroundings. The remaining part of the other than the system are called surroundings. So we have already studied in the open system, closed system and isolated system. So open system energy as well as mass can be transferred from system to surroundings, as well as in the closed system the energy can be transferred to surroundings from system to surrounding, but in this case mass cannot be leave it from the system to the surroundings. So isolated system. So isolated as well as adiabatic system. In the case of adiabatic system, neither heat or entered or leave from the system to surroundings. But in this case, in the case of isolated system, no energy as well as mass can be transformed. That is some important concept, thermodynamic concept of first law of thermodynamics. Now, what is the spontaneous reactions? Spontaneous reactions is actually represents the irreversible reactions. So the delta G value negative, delta H value negative, delta G value negative, but in the case delta S value will be positive for the spontaneous reactions. So for example, we can say the water flow from higher level to the from hill station to the lower station. So these are the examples of spontaneous reactions. Spontaneous reactions are irreversible reactions. Non-spontaneous reactions are reversible reactions like chemical reactions. So in the case of isolated system, the first law is actually failed to explain some of the concept in the case of isolated system. Energy of the system remains constant. So how the energy can be transferred from system to surroundings, that cannot be explained by the first law of thermodynamics. So we need for the second law of thermodynamics here. So energy of an isolated system remains constant during the reactions. Now Q is equal to W. So Q is equal to W means the amount of heat converted into amount of work. That is the first law of thermodynamics. But in this case, the second law says that the Q is not equal to W. So Q is not equal to W mentioned that the maximum amount of heat that can be converted into work. But all the heat absorbed by the system at particular temperature that cannot be converted into work completely without any dissipation of energy or without loss of any energy, without compensation of energy, that in the form of heat. Compensation means in the form of heat. Heat can be transformed during the reactions. Some of the chemical reaction may take place during the conservation of energy. So this is not explained by the first law of thermodynamics, so we need for the second law of thermodynamics here. So direction of flow of heat does not be explained by the first law of thermodynamics. Non-conservation of entropy. Entropy in the sense randomness or disorderness of the molecules. So randomness means every molecules in this universe become randomness. It will spread all over the air. Like if you assume that any one of the gas molecule, if you expand the gas molecule, it will spread all over the place other than the system. So whenever the calculation of entropy value will be positive for all the cases. So non-conservation of entropy here does not explain by the first law of thermodynamics. So dispersal of or degradation of energy of an isolated system. So isolated system, in the case isolated system, there is no dispersion of energy from system to surroundings. That is one of the concepts. So that not be explained by the first law of thermodynamics course. So we need for the second law of thermodynamics. Here the sum of the spontaneous reactions have been given. So one more point is the maximum amount of heat is converted into work. So how much amount of heat is converted into work, that is not explained on the basis of first law of thermodynamics. It can be explained by the second law. Spontaneous reactions, flow of heat from higher level to the lower level, or flow of potential, electrical potential from higher potential to lower potential. So electricity, heat flow from hot end to cold end. These are the some of the spontaneous reactions or irreversible reactions. Like spontaneous reactions can be explained the thermodynamical aspects like delta G value, delta H value, delta U value. All the value may be negative, or in the case some of the values will be 0, but in the case delta S equal to 0, that means the reverse reactions must be in equilibrium conditions. But if the delta S value is equal to negative, the reactions will not be taking place. Delta S equal to positive, the reactions is going to be spontaneous or irreversible reaction. That is one of the concept in thermodynamics. Some of the important concepts are available in the case of thermodynamics. Thermodynamics explains the flow of heat from one direction to the another direction. That is the direction will alone not explained by the first law of thermodynamics. Here also some of the concepts, some important isolated system and conservation of entropy. These are the very much important concepts in the first law of thermodynamics. But in this case, the second law tells the maximum amount of heat that can be converted into maximum amount of work. That is second law of thermodynamics. There are various statements of second law of thermodynamics. To calculate the second law of thermodynamics, one of the important concept here, Garner Theorem or Garner cycle. A cyclic engine is constructed which is a gas is allowed to expand 4 thermodynamic processes like expansion reactions of 2, adiabatic expansion and isothermal expansion reactions, as well as there are 2 compression reactions. There are 4 strokes of operation subjected to for a single ideal gaseous molecules. Like compression reactions, in this case they follow the same order, isothermal as well as adiabatic compression reactions. So in this case, expansion reaction, during the expansion reactions the work is done by the system, because the when you slightly pull the pressure, that means the system is the system is actually working, because the expansion reaction, the gaseous molecule will move along the any other directions. That means expansion reaction work is done by the system. But you compress the on the system, so work is done on the system. So whenever the work is done by the system, that is a negative value, because the energy must be lost during the expansion reaction. Though the W should be negative for the expansion reaction. In this case, compression reactions, the work is done by the system, so the value will W value will be positive. So these are the 4 strokes of operations. So what is a Garnot's actually? He constructed a machines. All the machines working between all the periodic machines, like we can say that any machines working between two same temperature must have the same efficiency. So whenever if the efficiency of the engine should be more, the eta is equal to 1, or the eta is not eta should be greater than 1. There are three kind of cases. The eta, the efficiency that is equal to 1, or it's greater than 1, or less than 1. So here they have constructed the machine. The efficiency of the engine can be calculated by using the different temperature, but the eta value is they got the value of less than 1, because the efficiency value will be always less than 1. Any machine working between the higher temperature, the maximum amount of heat is absorbed by the system. When the system undergo, or it can be done by the operation of the lower temperature, the system will absorb the heat and given out to the surroundings. So some of the heat must be lost during the reactions. That can be explained by the basis of Garner cycle or Garnot engine here. So what is a Garner theorem? Garner theorem says that all the periodic machines working between the any two same temperature must have the same efficiency. That is a Garner theorem. So the maximum amount of heat that can be converted into work. So all the machines or any machines working between the two temperature must have the same efficiency. That is a very important theorem, Garner theorem. He constructed one of the machine undergo cyclic process, 4 cycle, that known as Garner cycle. Here, if the efficiency should be greater than 1, what is the condition? So the temperature of the system, sink and source, so must be very much large difference. So source and sink temperature difference should be more, then only the eta have efficiency value is equal to unity or greater than 1. But it is does not depends upon what other substances are used in the cyclic process. The first law says that the conservation of energy, but here the Garner cycle says that it is independent of the nature of the substance which will involved in the cyclic process. It is depends upon the temperature difference of the source and sink. So if it is a higher temperature used of source and sink, the efficiency value will be greater than 1. Now let's see some more cyclic process like Garner cycle. In the second law of thermodynamics, there are two statements, Kelvin statement here, and as well as the Planck statement. Here the Kelvin statement says that it is impossible to extract heat from a reservoir without any consumption of energy. So it is impossible to extract heat from a reservoir without any transformation of energy that can be converted into equal amount of work. So Kelvin statement, one of the Kelvin statement says that it is impossible to heat converted into work. Impossible to heat that is converted into work without any consumption. So energy must be lost in the form of heat or in the form of any other way during the reaction. That can be says that the Garnot theorem, Garnot engines, all the periodic machines working between the any two same temperature must have the same efficiency. What is the meaning of efficiency? Efficiency is denoted by the symbol of eta, should be always less than 1. The efficiency is says that the fraction of heat absorbed that can be converted into work. That gives the efficiency of engine. The fraction of heat absorbed by the system that can be converted into equal amount of work, that is known as efficiency of engine. So here we now going to see a Garnot cycle, how the Garnot cycle is constructed, and 4 strokes of operation like isothermal expansion reaction and adiabatic expansion reaction. There are 2 compression reactions. Here in these equations we are going to calculate the W value. There are 4 work done by the system though. So net work done by the system and the amount of heat absorbed by the system we can calculate by using the formula Q2 and Q1. So heat absorbed, that is equal to work done by the system, that should give the value of heat as equal to unity, that means 1 in the form of value 1, but that the value we are going to calculate will not be equal to 1 because the temperature difference should be more between the source and sink. Now let's see the Garner cycle. Here the Garner cycle, I have drawn the how the cycle is complete the 4 series of operations, isothermal expansion reactions. In the isothermal expansion reactions, when a gas is allowed to expand at the temperature T2 here, the Q2 amount of heat is absorbed. So temperature T2, the Q2 amount of heat is absorbed. When the gas is allowed to expand, the volume of the gas increases from V1 to V2. So whenever the expansion reaction, the volume of the gas increases from V1 to V2 at temperature T2. So the value of W work done calculated by the system is equal to negative. That means W1 calculated. When the system undergoes then adiabatic expansion reaction, during the adiabatic process neither heat entered or leave from the system to surroundings. So when the gas is allowed to expand at adiabatic expansion at temperature T1, here the delta U value calculated, there are 4 kinds of value. Delta U value is equal to 0. In all the process, delta value is equal to 0. Here the delta U value is equal to 0. Delta U is equal to minus W, but Q is equal to 0. But because when the adiabatic process, heat is neither entered or nor leave from the system to surroundings, so Q value is equal to 0, delta U is equal to Cv into dt, Cv into delta T. That is the difference between the temperature T1 to T2. Here also the volume of gases expansion from V2 to V3. So W2 is calculated as minus W2 here, and then when the gas is allowed to compress, so work is done by the system. That means here the expansion reactions, there are 2 expansion reaction, work is done by the system, but you undergo the 3rd cyclic of operation, compression reaction like isothermal compression and adiabatic compression reactions. So here the isothermal compression reactions, the volume of the gas decreases from V3 to V4. So volume of the gas compressed V3 to V4 at a temperature as calculated as T2. Here the one more process is adiabatic expansion reaction. So since here the delta U value is equal to 0, here the Q value is equal to 0. In the adiabatic compression reactions, the Q1 value can be calculated. Here the W1, W2, W3, W4. The overall process is here the Q value of T2 and Q value of T1 has been calculated, because the how much amount of heat is absorbed by the system that can be converted into work, that's calculated by the efficiency of heat engine, that is a Carnot engine. This cyclic is actually used to calculate the amount of heat absorbed, that is equal to converted into amount of work. So in the case of expansion reaction, first one is isothermal. So isothermal expansion reactions, first one, the point is when a gas is allowed to expand reversibly and isothermally, the volume of a gas increases since delta U value is equal to 0, that Q is equal to minus W. Here the minus W1 become minus W1 at temperature T2. At T2 temperature here, so work done can be calculated by the system minus W1 is equal to Q2 is equal to R into T2 ln R into T2 ln V2 divided by V1. isothermal expansion reaction. Here the expansion reactions. So the second process is adiabatic expansion. So here the adiabatic expansion reactions, del Q is equal to 0. Since adiabatic process Q is equal to 0, here we can calculate by using the 1. Put the number of the equation 1 here. Adiabatic expansion reactions, delta U is equal to, since minus W mentioned that the work is done by the system. So we know that from the first law of thermodynamics, Cv is equal to dou U divided by dou T at B. For calculating the value, this represented as equation 2. By calculating the value, dou U or delta U is equal to Cv into delta T. Delta T is the temperature difference between the two values. So dou U is equal to Cv into T1 minus T2 here. So delta U is equal to minus W2 is equal to minus, I put the minus here also, Cv into minus Cv into T2 minus T1. Here the temperature difference I have rearranged that way. That is why I have put the minus charge here also. Minus W2 is equal to minus Cv into T2 minus T1. Here the isothermal expansion and adiabatic expansion reactions we have discussed. Now isothermal compression and adiabatic compression reactions. So isothermal compression reactions. Here the isothermal compression reactions, when the gas is allowed to compress reversibly and isothermally at lower temperature T1. At the lower temperature T1 here, the work is done by the at T1. Work is done on the system. Work is done on the system. So minus Q1. Here the sum of the heat absorbed at a higher temperature and converted the some amount of heat to the surroundings when the temperature is lowered from T2 to T1. Here the Q1, I put the minus charge here because heat is converted to the surrounding, from system to surroundings. So W3 is equal to R into T1 ln V4 divided by V3. So here the one more concept is adiabatic compression reactions. This case adiabatic, the fourth process, this is a third process, then fourth one, adiabatic compression. Here the put the value of third equation, fourth. Adiabatic compression reactions. In the adiabatic compression reaction, finally, and gas is allowed to compress reversibly and converted into the original state of V1. Here, the volume becomes V1 after the 4 cyclic process is completed. So Q is equal to 0. At original volume V1, the temperatures become T2. So at T2 temperature, volume becomes V1. So it's reversibly it's comes to the original form of V1 at temperature T2. Here the W value will be positive because the work is done on the system. Since delta U is equal to CV into delta T, we know that equations from the first law of thermodynamics here. So W4 is equal to here Q is equal to 0. Since adiabatic process Q is equal to 0, delta U is equal to W. So W4 is equal to CV into T2 minus T1. Here they mention the equation number 5. There are 5 equations present here. Now we can calculate the net heat absorbed by the system and the net work done converted by the system. Here there are 4 equations we have discussed here. Now net heat of reactions is observed, that is Q is equal to Q2 minus Q1. What is the Q2 value? R into T2 ln V2 divided by V1 minus R into T1, because the Q1 value is also negative, R into T1 ln V4 divided by V3. So the net work done given by the system here minus W1 minus W2 plus W3 W4, because these two are adiabatic and isothermal compression reactions. These two are expansion reactions. That is why I put the minus charge here. Work is done by the system. Here the work is done on the system. So W1, the value, just apply the value into the first equation into these equations of 6th. So R into T1, R into T2 ln V2 divided by V1 minus W2 CV into T2 minus T1 plus R into T1 ln V4 divided by V3. So W3 value and W4 value will be CV into T2 minus T1 here. These two values are cancelled to each other because gets the minus and plus value. So what is the remaining in equations? R into T2 ln V2 divided by V1 minus R into T1 ln V4 divided by V3. So V2 divided by V1 is equal to V3 divided by V4, because if you cancel the value or replace the R into T2 minus T1 here, so these two are become equal. So I have put the equation like this: W is equal to R into T2 minus T1. So R into T2 minus R into T1. There are two from R into T2 minus T1 ln V2 divided by V1, because these two are equal. So V2 divided by V1. Since Q2 amount of heat absorbed at temperature T2 is given by the equations, Q2 is equal to R into T2 ln V2 divided by V1. So if you dividing this equation W by Q2, what is the remaining in R? The R is cancelled, T2 here. T2 minus T1 is I have written here the W divided by Q2 is equal to T2 minus T1 divided by T2. These two are cancelled to each other. So it gives the value of efficiency. Eta is always less than 1. So W should be work done that must be less than the heat absorbed, because from this statement we know that the amount of heat absorbed that cannot be converted into equal amount of, that is the second law of thermodynamics, because the system can absorb heat at higher temperature T2. When it converted into lower temperature T1, some amount of heat liberated during the reactions. As well as the first law does not explain the chemical reaction. What are the chemical reactions taking place during the cyclic process is actually explained in the uses of Garner cycle theorem. Thank you.